So this is turning out to be a really amazing event. I'm glad to be here. I'm really glad that this event is happening this year. One thing I don't have a good sense of is where all the audience is with regards to how many of you are newbie Python programmers and how many of you are very experienced Python programmers. This is a talk that I put together. Is that better? Yeah, this is a talk that I put together called Top to Down, Left to Right. And it's a little bit about Python. So we're at PyData Warsaw. It's Friday, October 20th, 2017. My name is James Powell. If you like this talk, you can follow me on Twitter. I'm Don't Use This Code on Twitter. I'm also Don't Use This Code on GitHub and a lot of other places. I'm going to sit down for the rest of this talk because there's a lot of typing involved. This is by the way, fair warning, this is a novice talk, and this is a pure Python talk. So if you know everything there is to know about Python, this won't be very interesting to you. If you don't really care about Python, like you're an R programmer, this really won't matter to you. Do we have any R programmers in here who are just watching these talks out of pure spite? Okay, good. This is part of a series of talks that I've wanted to give about what is it that the audience doesn't know, that they don't know about Python. So a couple of things that even people who've been using Python for a while might be a little bit surprised about. What I want to do is I want to start you off with a couple of questions. Then I'll give you about 3 minutes of theory that'll explain all of the answers to all the questions. Then we'll go through all the answers. As I go through the questions, I'm going to need your immediate feedback to get a sense for what is it that you know and what is it that you don't know. So let's launch into it really quickly. I have two scripts, top and the bottom pane. From math, import log, import e, log of e. In the bottom, import math, math.log, math.e. What's the difference between these two? Just shout it out if you have any idea. What's the difference? We don't have much time, so you're going to have to shout really loudly, really energetically. One's shorter, one's maybe clearer, one uses a namespace. Does anyone else see any difference between the two of these? Nope? Okay, let's move on. This is a very simple exercise. I want you to shout out valid if what I show on the screen is valid Python code, invalid if what I show on the screen is invalid Python code, and if you hear somebody say the wrong answer, shout out wrong, just so I know that there's some disagreement. Python 3. This entire talk is in Python 3.7. Just because, yeah, whatever, right? Valid or invalid? Valid or invalid? Valid or invalid? Wrong. That one's valid. Valid or invalid? Valid or invalid? Everyone thinks it's valid? Anyone hear any wrong answers? Be sure to shout out wrong so I know there's disagreement. Let's do this next one here. Valid or invalid? Invalid. Valid. Somebody has a right or wrong answer. How about this last one here? Who thinks it's valid? Who thinks it's invalid? Who thinks it's valid but useless? That's the right answer. Let's also cover a couple of, let's make sure that you have a little bit of background information. So I have X, I have Y. They're two lists. Is X equal to Y, true or false? X is equal to Y, true. They have the same contents. X is Y, true or false? False. They are different objects, very good. So if I append 4 to X, does it show up in Y? No, they're different objects. If I append 4 to X, it will, of course, not show up in Y. Similarly, if I look at the IDs of X and Y, are they the same ID or different IDs? Different, very good. You guys are real smart. Let's take a look at a very similar problem. X and Y, are they equal to each other? Yes. Are they the same object? Yes. Very good. So if I append 4 to X, does it show up in Y? Yes. Very good. What about their IDs? They're the same. Okay, very good. So you won't have too much difficulty with the rest. Now, let's say I have code that looks like this. At the bottom is a script that imports the module at the top. What gets printed? Does called f get printed when I run the script below? No. Does defined f get printed when I run the script below? What if I add this code? Does define G get printed? Who says yes? We got to shoot from the hip. We don't have a lot of time to think in this talk, so who says no? Who says only defined F gets printed? Who thinks that when I add in these two lines, there's not a lot of code here, and I add in these two lines, the output of script.py changes? Who thinks it remains the same? Nobody thinks it changes? A couple people think it's changed. Good. A couple of you have used Flask or other tools that have module reloading. You ever wonder why it is that when you change something on disk, you have to shut down your Python interpreter and start it back up, or even restart your Jupyter kernel just to see those changes? Why can't Python be smarter? Why can't Python realize the file changed on disk, just reload everything? Let's take a look at an example relating to that. I have class A and class B. I have a script below, from module import A, create an instance of that. Is A an instance of the class A? Gotta shout it out. Yes. You can shout it out in English, Polish, I'll take any language. Is B an instance of the class B? Yes, no? Yes, of course it is. ImportLib has a tool called reload that allows you to reload modules. Is A still an instance of A after I reload this module? Is B still an instance of B? How about if I write the code like this? The answer might surprise you. Let's take a look at the last two examples. A remains an instance of A, but B is no longer an instance of B. And then in the last snippet of code, they're neither instances of the class themselves. So we'll go over a little bit of theory to figure out why it is that the answers to this are true, false, this is false, and false. It might surprise you. Okay, let's imagine that we're writing a little bit of code. Maybe we're the best Python programmer in our company, and we're at that company in order to show people how to really write proper Python code. So we write a class. And we need to add a little bit of data to that class, maybe an attribute called B. Except B, for some reason or other, can never be negative. So if somebody tries to set B to a negative number, we need to provide some error as quickly as possible. You have a coworker who's a Java programmer and tells you, well, that's a setter and a getter. What do you tell that coworker? It's not very Pythonic, because what do we have in Python that allows us to avoid this pattern? Property. Very good. So you say, write something like this. Use a property, and it'll intercept the set attribute and the get attribute, and it'll just work. You don't have to write setters and getters. And when your main code looks like this, it'll just work. And if I accidentally try and set this to a negative number, this line here will raise an error telling me the value must be positive. Everybody's in agreement. That's how you write proper Python code. Let's say we have a module, and that module has a constant in it called A. And we have some script that alters that constant, maybe sets it to 1. What if that constant can never be negative? We have to write a getter and a setter, don't we? Can we get around this? So you see there's a break in this pattern. For a normal Python object, we'd use a property to get around having to write getters and setters. But you must have seen this pattern on modules before, where people, again, have to write boring getters and setters to intercept changes to the module itself. Maybe there's a better way. Let's look at another problem. And I think this is the second to last problem we'll look at. What gets printed when I run the highlighted lines? It's a list. What are the contents of that list? 0. Very good. What if I add in this next line here? Does it print the same thing? Does it print something different? 0, 1. Very good. Some people have heard of this problem. It's often called mutable default arguments. What happens when the third line gets printed? 0, 1, 2? That's kind of curious. This is a problem called mutable default arguments. When a default argument is mutable, some of the behavior might not be what you expect, which is why if you go into Stack Overflow and you look up this problem, you'll see somebody propose an answer that looks like this. Set x equal to none, and then inside the function check is x none, and set it to the default value if x is none. Here, what gets printed with the first line? 0. What gets printed when I look at all 3 lines? 0, 0, 0. Probably what I expected. Let's take the original code up here, and let's just nest it in one more layer of a function. What gets printed when I run this? Is it 0, 0, 0, or is it 0, 0, 1, 0, 1, 2? Some people say 0, 0, 0. Does anyone say 0, 0, 1, 0, 1, 2? Let's take a look. OK, 0, 0, 0. That seems to be another way we could fix this problem. How about here? That kind of looks like a decorator. If I look at this, this kind of looks like what I do for a decorator. So if I create a decorator that looks like that, and I run the code in this fashion, what gets printed? 0, 0, 0, or 0, 0, 1, 0, 1, 2? 0, 1, OK. Very good. That's exactly what gets printed. What happens if I stick this into a class? Does that change the output? Which of the 2 outputs do I get? I don't know. All zeros, or 0, 0, 0, 0, 0, or 0, 0, 1, 0, 1, 2? Did I avoid my mutable default arguments or not? I did not avoid this problem. What happens if I just make that a normal instance method? Does that have any effect whatsoever? Each time so do I get 0, 0, 0, or 0, 0, 1, 0, 1, 2? 0, 0, 0, 0, 1, 0, 1, 2. Something's kind of funny here. Let's look at the last problem that we're going to solve. Some of you know that there is a built-in function called locals, and it gives you all the local variables that you have in scope. So there's not much in this script that runs. You can see there's a bunch of default variables: name, file, package, annotations, built-ins. You might know there's also a variable called globals. In the case of a script like this, the globals and the locals are the same thing. You can see from this line here, the locals is the same as the globals. So that just gives me all my local and all my global variables. So if I say, here's my old locals, I define x, will that show up? If I look at the difference between my locals after the definition and before the definition, will I see anything new? I should. I defined a variable. Well, interestingly enough, I don't see anything new. Why might that be? Well, it's the case that this locals is not a copy of all the local variables, but the actual current dictionary of all the local variables. So I might need to make a copy just to see that change. Here I capture what are my local variables before, make a copy of all those names, and then I'll print out the difference, and I can see, oh, this y variable got created. Pretty simple. What does this print? Anybody else? There's only a couple options. It doesn't print anything or it prints 10. So who thinks it doesn't print anything? Who thinks it doesn't print 10? How many R programmers here are like, I have no clue what's going on? OK. It prints 10. Pretty easy. What does this print? Hopefully more than one person can answer what this prints. What does this print? 10. Very good. What does this print? Good, the confidence level is rising. What does this print? Name error. Wrong answer, wrong answer. What does this print? 10 or 100? Prints 10. Had no effect whatsoever. That's kind of weird. So maybe it's a global. What does this print? Does this work? It works and it prints 100. Wait a moment, something's really weird. Python must be incredibly complicated for all these different behaviors to show up like this. What does this print? I'll give you three choices, 10, 1, and 100. This is your basic closure. Which of these three does it print? 10, 1, or 100? 100? Anyone think it prints 1? Anyone think it prints 10? Prints 10. What does this print? What error? Very good. It doesn't print 11. It prints unbound local error. That's kind of weird. Finally, and this is the last question I have, we have a bunch of statements in the Python grammar, while, for, with, def, class. Two of these statements, two of the things that would show up in yellow on my screen, have no corresponding executable code. Does anyone know what they are? Actually, yeah, 3 of them, so including pass. So what else other than pass? Okay, we'll talk about that. Okay, so let's talk about the theory. There's very little theory behind this. The reason I like this talk and the reason I like this topic is I showed you an enormous amount of behavior which you couldn't immediately guess the answer to. And it seemed like the model for how Python worked must be very complicated. It seemed like all the operation of the Python interpreter, it's like a flashback to when you were writing C++. There's no way that you could understand how the Python interpreter worked. But you're wrong. The Python interpreter has an incredibly simple execution model, and I'm going to give you about 5 minutes of theory to explain how that execution model works, and then the answer to every one of those questions will be clear as day. In order to do that, I need to introduce something. There is a function in a module in the standard library called dis. Let's see what it does. It disassembles classes, methods, functions, generators, or code. Okay, so it shows me what the bytecode that runs in a CPython interpreter for a given piece of code. So let me try and disassemble len. Oh, I can't disassemble len. So I can only disassemble Python functions. It can only give me bytecode for things that are written in Python. It can't give me bytecode for functions written in C, like the built-in function len. So let me try and disassemble this function here. Well, that's interesting. So there's a little bit of data on my screen. This 3 here is the line number for the corresponding bytecode it's printing out. So line 1, 2, 3. So this is the bytecode for pass. Well, you know that a function that has no body just returns none. So what does it do? It loads the constant none, and it returns that value. You can kind of see what it does. It loads a value and returns it. The number in this column over here is the offset for the bytecode. So you can say that load const is probably 2 bytes long. You can't tell me how long return value is, but it's, I think, only 1 or 2 bytes long. This value here is the actual argument for that opcode, and in parentheses is the interpretation of that. So this load const had an argument 0, which you can interpret as the constant value none. We'll see what that means in a second. Let's disassemble this function and see what it looks like. Well, it load fast, so I don't know what fast means, but I know what load means. It loads the variable x, it loads the variable y, it does a binary add. Well, yeah, it does. It adds 2 things together, and it returns that value. Okay, pretty simple. So the bytecode actually is quite easy for me to read. Let's take a look at disassembling a class. Wait a second, it doesn't print anything at all. It's kind of weird. Let's wrap this in a function and then try and disassemble it. Okay, I got something here, so let's see what it did. It load build class. I wonder what that is. It loaded a constant value, and that constant value was a code object sitting at some port in memory named A in some file standard in. It loaded a constant, the name A. It called this thing called make function. It loaded another constant. It did a bytecode called call function. It stored that to the variable A. It loaded none, and it returned it, because this function returns none. So that's interesting. Let's do the same thing with the function. Let's see what happens here. I loaded some constant, some code object. I loaded some constant, which is just a string with the name f in it. I did this thing called make function. I stored it to the variable f, and I didn't return anything. Okay. Let's take a module that looks like this. It just has a function that was defined and a class that was defined. And let's try and disassemble that function. Or sorry, disassemble that module. Well, you can see it went in and tried to disassemble each of the constituent parts. So nothing too different than what I saw before. Finally, let's take a closer look at what happens when I define a function. I load some constant. I call this bytecode make function. and I store the result to the variable f. Let's see what happens when I define a class. I do a couple of extra steps, but I still have some code object somewhere. I still have some call function somewhere, and I store the result to A. What you can see from this is when the Python interpreter comes across a statement def or a statement class, this is actually executable code. In a language like Java or C or C++, class and function definitions do not exist at runtime. They get turned into just a bag of bits in the compiler in C. So the C compiler will turn a function definition to a bag of bits, and maybe if you have debugging options added on, you can actually figure out what that function is. But otherwise, there's no corresponding runtime execution of the definition of a function. But Python's different. When you see a function definition or a class definition, Python actually does executable runtime steps to define that. So if we go back to the very first question about what was valid and what isn't valid, I can define a class in a for loop. It just defines the class over and over and over, because each of those def statements is just some code that runs. I can define a class in a for loop. It just defines the same class over and over and over and stores it back to the same variable name. It works, but it's pretty useless. Let's take a look at this a little bit closer. And let's look at disassembling a couple of things. Here I have a global variable. Let's disassemble a function that uses this global variable. I see this load global of x here. Okay, kind of makes sense. It's a global variable, so I should have a load global. It's not too fancy. Let's do the same thing with the local variable. I have load fast, so I guess fast must mean local variable. That's kind of interesting. Let's see what happens if it has a default argument. No change whatsoever, so I again see a load fast. So if it's a local variable with the default argument or not, they both turn into load fast. Let's see what happens if I do this kind of closure structure, and I have the x on the inner function refer to an x defined in some outer function. I see load deref, so I guess deref must mean closure. And let's see what happens if I have a constant value. Oh, load const. Okay. So I know there's different types of loads: global, local, constant, and closure, or deref. Let's take a look at a function that takes two variables, x and y. What are the types of x and y? Anything. What does a bytecode get generated from this? Binary add. Does Python know if these are two integers or two strings or two objects? Does Python know if these things can even be added? Nope. It defers all of that to runtime. So Python just sees some name x referring to some object, some name y referring to some object, and it waits until this line is executed to try to binary add them and do something with that. And if it works, it works. If it doesn't work, it fails. But you have no static knowledge about whether that'll work or not. Similarly, if I call x as though it were a function, let's take a look at the bytecode. Turns into call function. So that's what that call function was. It said you had a function and you just invoke that function. Does Python know if that's a function or a class or a type or a module or an object or something that can't even be called? Nope. Python just waits until you try to do something with it, and it gives you an error if that operation isn't supported. Let's say I do an attribute lookup. Does Python know? Let's take a look at the disassembly for this. You can see a load adder, so I'm trying to load an attribute. Does Python know if the attribute A exists on the object X? Does Python even know what X is? Does Python know if X has any attributes that I could grab? Nope. It just waits until runtime and tries it. And as we start to disassemble more and more things, we'll see this pattern recur. Python is a language that defers a lot of decision making to the runtime. It has a very small, almost useless compile time. But there is a compile time, and we'll see in just 1 second what happens at compile time. Fundamentally, Python runs code from top to bottom, left to right. Classes and function definitions are just executable code. When it sees a function definition, it grabs all the stuff under that function definition, turns that into bytecode, and it, every time that function is defined, turns that bytecode, wraps it with the function name, and creates a new function of that type. Same thing with classes. That's why I can define classes in a loop. I can define functions in a loop. Also, a lot of the core syntax of Python is as simple as just doing load attribute, get attribute, or binary or binary operations. And in that core syntax, Python has no idea until that line is run that the object that it's operating on is a class versus a type versus whatever. In this case, notice, Python does not even know. X could be a module. If I change this to math.a, Python does a load adder just as though it were an object. So what we can see is that in that very first example, where the difference between the imports, in the second example, when I did math.log and math.e, I'm just doing an attribute lookup on some object. And there's meaning to when you do an attribute lookup on some object. Let's take a look at the last piece of theory that we need to talk about. I'll show you how Python actually runs code. When you say import module, Python goes and it finds module.py, or it finds a folder that contains an init.py, but eventually it finds some .py file, and it reads it in. So it runs code that looks something, whoops. It runs code that looks something like this. And you can see this is the source code of my module. My module is just like before. It has an F and an A. It just reads it in. This is just a string. Then it parses it. So let's take a look at what happens in the parse step. I get an AST. So it just turns that source code, tokenizes it, turns it into an AST. And that AST has a body, and you can see in the body of this there's a function definition and a class definition. Let's look at the function definition. Let's look at the body of that function definition. It's got a return. Notice this thing, all it did was it returned one thing. Let's look at the value that it returns. It's a binary operation. Let's look at the left-hand side of that binary operation. It's a name. It's a name X. Let's look at the right-hand side. It's the name Y. Pretty simple. This is just an AST that encodes this same information, subject to checking that the syntax is correct and putting it into a structure that can then be passed to the next step, which is the compiler. The Python compiler takes this AST and it creates a code object. Let's see what that looks like. Just some code object here, and let's see what the code object contains. Well, it contains the actual bytecode itself, and so you can see if I disassemble, you can see there's 24 plus whatever the size of return value in this code object. That's about 24 bytes here. The code object also contains some other interesting information. Code.coname, the name of the function itself, the names of any local variables, the number of local variables, and some other information as well, some flags, and so on. After it constructs the code object, it executes that code object, and it needs to evaluate it. And it creates a namespace, which is basically just a dictionary, and it just executes that code in the namespace. So let's look at the namespace after executing my module. Well, let's look at its keys, and it just contains the function I defined F and the class that I defined A. Now, you know, a namespace by itself isn't very useful, so we need to construct a module. And a Python module is just some arbitrary Python object that has a name, has some lookup mechanism, and has the ability to look up the contents inside. So I simulated that by just updating the dictionary of this object with the contents of the module. So let's run that and take a look. So here I have my module, and if I do module.a or module.f, I get the contents of that module. And then finally, somebody tries to use that module. So you might write something like f equals module.f. We'll call that binding. And then you might call the function f. And if you remember, the function f just adds two things together. Okay? So that leads us to something very interesting. The import statement in Python does not execute code. The import statement in Python brings a name into scope. When you say from module import f, that's the same thing as saying, give me access to the module, in this case named module, and say f equals module.f. It binds f. When you say import module, there is no execution of code. It brings the name module into scope by doing something that looks like this. Go to sys.modules, look up the module that I want, say module equals that. Maybe I'll give it a slightly different name so that this might be a little bit clearer. Okay? The execution of code only happens as a side effect of when Python cannot find the module in sys.modules. Let's go back and let's answer every question. And think about this in very simplistic terms. Everything operates top down, left to right. Before we do that, I want to show you two small things. This is the Python compiler itself. In the Python compiler, there is a function called compiler nameup. When Python code is compiled, the Python compiler determines where the variables come from. So it can emit either a load fast, load global, load deref, or other load operation. It determines that by looking at the static source text and figuring out where was x defined. And it knows x is defined by either a statement that says x equals, class x, for x in something, with something as x, accept something as x, and so on. There's only a finite number, I think 7 or 8 ways that a variable can come into scope. Python can statically determine all of those and then determine, is this a local variable, a global variable, a closure variable, and emit bytecode. When you see a load fast variable, what it does is it loads it fast. It loads this variable from a tuple that's stored attached to a frame. When it loads a constant variable, it pulls that from a tuple of all the constant variables that are collected at parse time. When it loads a deref, it goes and finds the closure and then pulls it from the closure. So let's go back and answer all of our questions. There is a meaningful difference between the two of these, but it is very subtle. In the top, you bind the value of log and e early, which means if some joker went in and did this, on line 7, you'd see the same result that you saw on line 2, because you captured the value of log and the value of e as of line 1, and no subsequent changes to that module will take effect. Here, if some joker tries to do the same thing, line 7 does an attribute lookup, just like any other object, looks up the current value of log, looks up the current value of e, and your joker will have his day. This is why when you're told to append your path in Python, this works. This operates on the actual sys.path, and it actually fixes your sys.path. This does not work. What you accidentally did was you bound the value of path early. Then, in your local scope, you just created a new shadowed version of the sys.path. This works because even though you bound the value of path early, you performed a mutating operation on the original path, so this just works. And this works because you're looking up, sorry, this should be sys.path. You're looking up the current version of path and then setting the current version of path. That's why we see this difference. Let's look at the module. When this module is imported for the very first time, and by the way, you may not be able to, in a very large system, deterministically, you may not be able to casually determine when a module is first imported in a very large system, especially if your code is over here and some bootstrap code or some initialization code is over here. Your module could have been imported at any time in the process, and it turns out that your there are certain configuration options that can load modules. Your site flags or your site options can, in some cases, load a bunch of modules that you might not even realize are being loaded. So you might not actually know when a module is imported. So you might not actually know when a module is executed. In the script below, that module is only ever executed once. It is executed from top to bottom, left to right. The very first time this module is executed, all 3 of those define statements are printed out to the screen. Doesn't matter if you import F from the module or G from the module or H from the module. Some people, when they look at this, they say, well, if I import just log and E from math, I use less memory because I don't pull in the other stuff. Nope. Python always runs modules in their entirety from top to bottom. Why? Because you could always, at the bottom of the module, have a for loop that defines some function many times. Python has no way to determine statically where a function or where a class is defined. It could be defined by some arbitrarily complex executable code. And as a consequence, the only option the Python interpreter ever has is to always run modules from top to bottom, left to right, every single time they get executed. However, As an optimization, we only execute it the very first time it's imported. This is why you can't execute or load only certain portions of modules. You always grab the whole module at the same time. This is also why, in this case, you had different answers. Here, the first two are obvious, but here we reloaded the module. Notice that the A here is the A that I early bound on line 3. So the lowercase a, the A instance, is still an instance of the class that was early bound on line 3. But on line 17, I look up the current version of B in the current reloaded module, which will have been re-executed, and it is no longer the original B that constructed the instance B on line 17. And on line 19, I pull out the current version of A and B from that module, and the original A instance and B instance are completely different than were constructed by types completely different than the types that sit in that module right now. This is why arbitrary code reloading does not work in Python. You'll suddenly run into all sorts of very weird errors where things are no longer instances of things you expect. And it only works in very limited domains where you can patch all of the objects in your system to whatever the new versions that were loaded by the module are. That's why the hot code reloading in a tool like Flask or Django can sometimes break in very strange ways if its hot code reloader doesn't know how to patch old objects to the new definitions. Let's take a look at this. Well, here's what I know. When I do, actually, let's take a look at our module. When I do module.a, that's just a load attribute, right? And so a module is just an object that I can't easily construct. But the answer to this is quite easy. Let's make B a property and say b.setter. And then in my module, I'll say if my name is not main, if I'm importing this thing as a module, what I'll do is I'll go into sys.modules and I'll grab myself. I'll grab the thing that I was supposed to be. I'll grab the type of it. I'll grab the contents of it. I'll grab all of the contents that happen to be properties. And I'll create a new class with all of the properties. I'll create a new instance of the module type, and then I'll copy everything over. It is possible to do module level properties in Python. It's only about 7 or 8 lines of code. And what you're doing is you're just understanding that module.a is an attribute lookup than any other attribute lookup. So the key to making this work is just be able to create your own module type. Let's look at mutable default arguments. This code is executed top to bottom, left to right. This line is executed. This line, these two lines are parsed, turned into bytecode, and then stored in that code object. So when line 3 is executed, you would create one list that gets reused every time. That's why this uses the same list as this, because that list is only ever constructed once. However, when I do this, notice the list is constructed as part of the execution of the function, so a new list is used every time. When I wrap this in a wrapped function, notice that this function is re-executed every time the outer function is executed, so a new list is used every single time. When I try this with the decorator syntax, it doesn't work because this line is executed once, and it doesn't matter what happened in this decorator. What matters is how many times do I execute that top line of that function, which is only once. So this retains the bad behavior. When I stick this into a class, the body of a class is executed and put into a namespace and then stored on the type. And so this gets executed once under this namespace. So the bad behavior is retained. Same in this case. Let's take a look at our scope problem. Z is a global variable. The Python interpreter does not know where the Z in this line comes from, so it'll assume by default it's a global variable. In a module scope, the locals and the globals are the same object, so this just works. I don't even have to execute it. Here, well, that doesn't do anything interesting. Here, Python sees an X variable. It tries to figure out where did that X variable come from. It can't see an X equals anywhere here. It can't arbitrarily go into this code because you could make this arbitrarily complicated, right? So Python won't execute anything to figure out. It'll just look for a line that says X equals or import X or import or from Y import X. There's only a set number of ways you can bring a variable into scope, or from Y import Z as X, or with something as X, or for X in something, or except, if you're an exception, something as X. There's only a couple ways you can create an X variable. So it'll look for all of those. It won't find them. It'll say, oh, well, X must be a global variable. And this change to locals won't be picked up. When we disassemble this, we'll see that Python assumed statically that this was a global variable. This is the only thing the Python compiler does that's interesting at all. It figures out where variables come from in order to optimize variable lookup. It'll assume statically X is a global variable, and the change to locals won't have effect. Here, we see something interesting. When we look at that load fast, it didn't read from globals. Sorry, it didn't read from locals. It read from a special array that's attached to the frame object. So this will have no effect whatsoever. Here, this works because Python cannot find where that X variable comes from. It assumes it's a global variable. And the reason it assumes things are global variables is you could have something like this. And so by default, that's the last place you look. It's probably a global variable, and if you can't find the execution, it was probably an import star operation that occurred somewhere that made everything very hard to find. So this works. Python assumes it's a global variable, and it actually looks in the globals dictionary and finds the value you want. Here, Python knows this is a closure variable because it can see it up here. So this won't work, and this won't work, because that's not where Python's looking for the variable. Finally, in this example, what Python thinks this line says is that. Python thinks there's a local variable X because you said X equals. When it tries to evaluate this line, it tries to use the local variable X that it knows exists in this scope. But it doesn't exist until this line has completed execution. So Python won't even look up to the closure to find it. So the solution for this is non-local X. I told you there are two. There's actually three non-executable Python statements. They are global, non-local, and of course pass. Now pass isn't very interesting, but global and non-local are interesting. All they do is they tell the Python interpreter where the variable came from. There's no corresponding bytecode for non-local or global. They're just hints to the Python interpreter that, hey, you can't find this variable, I'll tell you where it comes from. It comes from the dereference scope, it comes from the global scope. And it just guides the Python interpreter into emitting the correct bytecode. And that's the end of our questions. So you can see with a very simple model for how Python works, if you don't overthink it, if you don't reach for the complexity of a language like C++ or Java in terms of their execution models, you can end up answering every single one of these questions, many of which seemed very perplexing at the beginning of this talk, with just a very simple mental model. Python interpreter only executes modules the first time they are imported. It executes them from top to bottom, left to right. The def statement or the class statement is part of the executable code. The body of that function is just turned into a code object. The def or the class statement are executable code. They correspond to, used to be make class and make function, but in Python 3 it's now make function to build a function and then two make functions to build a class. Don't ask, there's a simplification that we can talk about later. And that's it. And every one of these questions, which might lead you on Stack Overflow for hours and hours to pick up wrong or incorrect or overly complex mental models, are unnecessary. With one simple mental model, every one of these questions can be answered immediately and with sufficient nuance to really understand what your Python code does. So that was top down, left to right.